Thank you for introduction. I'm Masahiro Horibe from Japan, and I would like to introduce our strategy to create a global quantum business ecosystem. So the G-QuAT is a new center. It's we are now purchasing the two types of the quantum computers, and then so I support to introduce one quantum computer from domestic companies, and so yeah. Then our center is not only focusing on the research and development, but also the business creation. And in the so-called last outcome is creating a global quantum business ecosystem. So the business ecosystem not only contains the application development, but also the hardware development, HPC hybridization, so computing platform, everything, and including the supply chain. And then so this center is the contained development application, industry level valuable applications, and in the computing platform, also the quantum computing systems, and also industry level supply chain, everything. Then our on-premise quantum computer is strongly related to not only for the application development, but also the supply chain development and the next generation quantum computer development. Okay, all right. Okay, yes. So this is one of the picture, one of the strategies shown here. So we are now building up the headquarters building. It's now we are preparing HPC GPU HPC. It's constructed by the over 2,000 units of the NVIDIA H100 GPU. So this HPC is used for the quantum computing research. So then at the next building, so we will install the two types of quantum computers. It's a neutron atom from QLS and the superconductor type computer from Fujitsu. And also the two types of quantum computer, the criteria to installation is over 100 qubit systems. Then because we have to use the industrial use. And then otherwise optical photonic quantum computer will be installed by the Japanese startup, and so with the support to build up the quantum computer system and create the business using their own machines. And then the other important area is the hybridize the GPU HPCs and the realistic quantum computers, and this platform to provide the hybrid environment, hybrid algorithms, and creating a usability to access all quantum computers shown later. And the other important point in the second floor is now set up the incubation and collaboration areas. And we invite to the many startups. It's from the users, vendors, and the suppliers, and also the venture capital analysts. And we accelerate the collaboration to create new market, and also create next generation or next generation quantum computers. Okay, this is our 8 strategic activities shown here. So the global quantum business ecosystem needs to the global collaboration. And also we have to support. We are now the public sectors. So the private sector invests to the many startups, but the startups requires the environment to develop their solutions and then start the business. And so we support to them using our platform. And otherwise, supply chain creations, and also the collaboration incubation and the competition environment shown here. And finally, we establish a global ecosystem. Okay. And this is a strategy for the industry level use cases creations. And so AIST is our main body. It's the G-QuAT is a part of the AIST. AIST is the biggest research institute in Japan, and so AIST is working on the many industry sectors, and also collaborate with the end user companies. And so researchers working in each areas already use data analysis and the informatics technologies, and also access to the existing HPC technologies. But they are a little bit stressful because there's not enough performance of the HPCs, and so they require to the quantum algorithms and then the quantum computers. And so our center to prepare the quantum computers and the quantum algorithms and the quantum simulators and all solutions they give them. And they, the end user side, it's create a new solutions using a hybrid computing environment between the HPCs and the quantum technologies. And after achievement the new solutions, so our collaborators, the user company, it implement that achievement to their business, and so they create a market, and so the end user company get the money, they are happy, and then so they invest to the quantum areas. So this is an ecosystem, and so this is a user side ecosystem shown here, and then also we are now preparing the not here, yes. So we are now preparing the computing resources here. So here, and then also I mentioned the data, and so we are now support to develop next generation. What's the next generation quantum computers systems, and then so we are support to the suppliers and then so by our component test bed, and also we also have the fabrication infrastructures for the large-scale quantum computing chip, and then the cryo-electronics to control the qubit. And so all three test beds are open for users. Users means application users, end users, and the computing vendors and the suppliers, everything. And then, so this activity can not be done by ourselves, so that we need collaboration in the world. Yeah. And this is a strategy for the computing platform shown here. And then so recently, many startup companies released their own machine, and also users want to access everything, but so it's difficult to access everything because some interface is completely different, sometimes different, and then so the users set up their PCs, and then after that they can access the one system. And then so if they want to access other one, so they have to set up other interfaces. And so this is very tough work. So we are now preparing this type of platform. It's now we are preparing the HPC, GPU HPC is not only for the classical computing resources, but also gateway to access all quantum computers. And also we invite to the many computing vendors, and the users and the vendors is staying in the same site and the same place, and it's a very good atmosphere because the vendors have the very know-how to use the more efficient usage of their quantum computers, and that know-how to transfer to users. Users create very valuable and it's more efficient use cases. And then also users access all quantum computers in this platform, and then the users decide best way, and each users decided to their own best way, and after that, so this means created. And in the vendor users, between the vendor user side, they create the collaboration to create new solutions. And then so users sometimes feedback to technical issues, technical problem to the vendors. And the vendor plan to develop next generation quantum computers. And then also between the vendor side, so this environment create competitions. And then so each vendor invests their own money and to create to improve their machines. Okay. Yes. This is one of the idea of the software stack of the ABCI Q2 as a gateway So there is a many software stacks. And then so we are also collaborate with many stakeholders. So our GPU clusters. So every solution can be installed. And then so all users access everything. And then so also the users choose the best way to access quantum computers and the quantum simulators here. And as a result, we can get the well accessibility for users. So then this is so we are happy to collaborate everybody to create this type of the framework, and then so we establish a hybrid environment. So and then so try to make standardizations. Okay. Oh, next, please. Okay. Yeah. And in the little bit, I'd like to move to the little bit hardware side. And in the as you know, the last year, so several ECOP making announcement is done, and one of them is IBM reached to the 1,000 physical qubit system on one tips, and then the QuAT demonstrated the logical qubit operations, and then after that, so the quantum computing field. It's quantum computing is not only a research item, but also the research tool. It's so-called quantum utilities. It's from the IBM. And so our side is now trying to create the industrial level use cases and the industrial level quantum computers. Okay. Okay, and what is industrial level quantum computers? So this is an example of the superconducting type quantum computers. And so currently several hundred qubit system is shown here. So they use the very bulky cables and the very bulky component. It's not our efficient component used. And then so it's very difficult to expand qubit size. And then because we need more big dilutions, and that's not good power efficiencies. And then so currently IBM is now use flat cable technologies, and then so high density a component and so on here. And then but it reaches several thousand qubit system here. So the next generation shown here. This is just ideas. So we have to use the cryo-electronics technologies. Cryo-electronics contains not only the cryo CMOS, but the superconducting digital circuit, and then shown here. And then also almost all components have to be integrated in the one modules. And then so we design the RF module and the design for the whole quantum computing system. And also we need redesign the dilutions, and because we try to install the cryo-electronics technologies, so we need more high power cooling power at 4K or 10K or 30K stages. And then so we already redesigned the dilution systems. And so as a result, we can create the 10,000 or 100,000 qubit system in the one dilutions. This is our strategy here, shown here. Okay, and then so now we are now communicating to the Japanese government. So we are now creating the many types of new component used for the next generation quantum computers, shown here. So one of them is the flat cables, cryo-electronics shown here. And after that, this type of component used for the photonic quantum computers and the trapped ions and neutron atoms shown here. And shown here. And so after that, we can get next generation quantum computers. Okay. Okay, this is schematic view of how to develop next generation quantum computers. So there is two important part. One part is left hand, right hand side. This is creating or improvement or miniature improvement of the existing components. And left hand side is installing the new technology like as the cryo-electronics. Here. I'd like to explain the improvement of the existing technologies. So the existing technology, for example, cable and amplifiers and the components and so on, and the company already have the mass production and the quality control capabilities, but they don't have the testing environment. So then we are now preparing the testing environment, testing environment. So this is one example shown here. So that we are creating our original refrigerator system, and this system has the two called head, and in the whole example, its cable is set up between one side and the other side, and the one side is 30K, one side is 4K. We can measure the very realistic condition in the dilution of the superconducting type quantum computers. So this is one of the results of the cable loss measurements result. And in the other setup, we can measure the dielectric permittivity and then the loss tangent of the packaging materials from the 4K to the 300K. And at several frequencies now. And in we are now started to standardize this type of measurement method. And other activities shown here, we are now preparing the dilution type measurement system for the RF component and the optical components. And the other one is squeeze level evaluation system. It's used for the photonic quantum computers, and so here. Okay. And other activities not working here. Why? Okay. Yeah. The next activity is new technology implementations. So cryo-electronics technology, there is three types of cryo-electronic technology. One of them is cryo-CMOS technology, so this is widely used. And then the other one is superconducting data, two types of superconducting data circuit. One of them RSQ, other one AQFP. So each technology have the different power consumption. And so we are now design the system, control system using these three types of the combination of these three types of technologies. And in this, we already demonstrate the qubit control using the superconducting data circuit shown here. And in so we are now implementation, try to implement these technology to the next generation quantum computers. And also, this is the design capabilities. And also we have the fabrication capabilities. And we already established 11 niobium wiring technologies. And we can demonstrate some kind of digital circuit operated by operation frequency is over 30 gigahertz frequencies. And so we can design the control system to the qubit here. Okay, this is the last slide shown here. So our site, we are now installing the on-premise quantum computers. This is just a first step. So we are now also we are collaborating with the QuAT and Fujitsu and to create the next generation quantum computers using our technology and then the supplier technologies. And in each computer is produced to provide to the users create application, and they feed back to the technical problem, and so vendors they create the next generation quantum computer, collaborate with suppliers, and this is our ecosystem strategies, and so we need on-premise and so computer. So if this computer is online or was internet, it is impossible to access hardware. And so this is our on-premise quantum computer strategy. Thank you for your attention. That's the finish.